Have you ever wondered how can we generate electricity out of sunlight? Well, it's all thanks to something called the photovoltaic effect. To understand it, we need to learn a bit of quantum mechanics. Now, electrons are not stable, they can leap between shells in an atom. An electron needs an external source of energy to jump from a low shell to a higher one. And when it falls back, it releases the energy back out. Electrons always seek the lowest available shell, so the second shell won't start filling until the first one is completely filled. For example, silicon has 14 electrons, 2 in the first shell, 8 in the second one, which leaves only 4 for the third shell, or the outermost shell, which is called the valence shell. When multiple atoms come together in a substance, their combined valence shells form another space that electrons can occupy. It's called a conduction band. This band allows electrons to move freely, which is very important for generating a current. In insulators, which are neither good insulators or good conductors, the gap between bands is small, so the energy needed to jump through it is also small. That energy might be obtained from photons in sunlight. If a photon has enough energy, it gets absorbed by an electron. The energy from the photon excites the electron from the full valence band into the empty conduction band. The empty space it leaves behind in the atom is called a hole, and it carries a positive charge. The electron might fall back into its hole, emitting a photon in the process. In order to generate a current, which is a flow of electrons, we need to get a lot of electrons into the conduction band and prevent them from recombining with their hole before they go through an outer circuit. To do that, we take one side of a semiconductor, such as silicon, and replace a few of its atoms that have 4 valence electrons with phosphorus atoms that have 5 valence electrons, which leaves one electron free to move about the silicon substance at room temperature. That creates what's called an N-type semiconductor, as it has extra electrons with negative charges. Then we replace a few of the silicon atoms on the other side of the semiconductor with boron atoms, which only have 3 valence electrons. When they bond with the silicon atoms, they bond with 3 electrons, leaving one empty space or a hole in the substance. That hole might be filled by a neighboring electron, which leaves a hole in its original atom, and so on. So holes too can move around the semiconductor. This type of semiconductor is called a p-type semiconductor. The area where the p semiconductor and the n semiconductor combine is called a p-n junction. What happens next is that the free electrons from the n semiconductor move towards the p-type semiconductor, and holes in the p-type semiconductor move towards the n-type semiconductor. In the junction, electrons and holes recombine and they mutually neutralize. That leaves one phosphorus atom in the n side without one of its electrons, so it becomes a positive ion, which means it has one extra positive charge. On the other side, one boron atom gains an electron and becomes a negative ion, which means it has now one extra negative charge. This process creates a potential barrier between the n side and the p side, which stops the electrons and holes from recombining, as it requires particles to have a great amount of energy to pass through it. When we expose this semiconductor to sunlight, what happens is that energy from photons excites electrons from the valence band to the conduction band, which creates electron-hole pairs in the junction. Electrons get pushed to the n-type semiconductor because it has a net positive charge, and holes get pushed to the p-type semiconductor because it has a net negative charge. Therefore, we prevent them from recombining. When we connect the p-type semiconductor and the n-type semiconductor by an external circuit, electrons from the conduction band and the n-type semiconductor move through the conductive to the p-type semiconductor, where they recombine with holes, generating an electrical current in the process.